Okay, hi. This is Karthik. It's really sort of late, so I should apologize for that, but sort of under a time crunch these days, you know. So, last time we talked about the experimental foundations of quantum mechanics. Today we need to now talk about, or start developing the tools to talk about the mathematical framework of quantum mechanics, and that begins with the subject of linear algebra. So, this is kind of big name you've probably all heard before. And what is linear algebra? Roughly, linear algebra is going to be studies of... Okay, let's get this to work. Linear algebra is going to be the study of spaces where linearity, in some kind of quotations, makes sense, and linear maps on these spaces. So basically, these kinds of spaces where we have this notion of linearity and then these actual linear sort of objects on top of that. And so the linear algebra stuff that I've taken this theory out of, it's out of some theory notes from my teacher. Some of this is out of Axler's book. Some of this is out of Halmos's book. There is a ChatGPT appendix on matrix theory, which is useful for calculating things in linear algebra. If you don't already know matrix theory, you can look at that, and if it's incorrect, or if it doesn't make sense, which it might, because it's ChatGPT, feel free to ask me, and I will go through and explain it to you. We don't have time to cover it in class, though. So maybe we should start by actually talking about what are these spaces. So, 2.1, vector spaces. And so, let's make a definition. Let R or C be real complex numbers respectively. Vector space over R or respectively C is a set V with operations, and so we're going to have an addition operation, V cross V to V and VW to V plus W, and we're going to have a multiplication operation, and this addition operation is going to, it looks very similar towards the addition you see on the sets. This multiplication will not. This is going to be a multiplication not from V cross V, but R cross V to C, or to V, or equivalently in the case of the field being C, we're going to say this is C, not R, and this sends a pair CV to CV, so we just denote multiplication like that. This is called vector addition, and this is called scalar multiplication. Equivalently, we sort of say V is the space of vectors, R or C is the space of scalars, and these satisfy the following axioms. So for addition, we have U plus V plus W equals U plus V plus W. So this is going to be A1. A2, we're going to have commutativity, U plus V equals V plus U. A3, there exists 0 in V such that V plus 0 equals V equals 0 plus V for every V in V. Equals V equals 0 plus V for every V in V. And we're going to have A4. For every V in V, there exists some kind of inverse of V, let's call it W, such that V plus W equals 0. And those of you who have been doing a good job and have been doing your sets will notice that this is exactly the axioms of the multiplication in a ring. But this is not quite a ring. Let's look at the multiplication. The multiplication has the same sort of associativity rule. XY on V equals X on YV for XY in the field R and V in the vector space V. So this is going to be S1. S2 is going to say we have distributivity. S3 is going to say we have scalar addition. So X, V plus W. And so this is distributivity of the scalars, this is going to be distributed over the vectors, because these guys live in V, these guys live in R. And this is in V, and this is in R. So here, this is a distributive law with respect to the scalars. This is going to be a distributive law with respect to the vectors. And finally, we have a rule that for 1 in R, 1V equals V for every V in V. And so this multiplication is kind of sort of different from the one we see on the sets. Most importantly, of course, being that it is not from V to V. It is not an operation from the set into itself. It is an operation of this scalar space onto this vector space. And so what are the examples? And there is one very natural example that is going to come up, and that's going to be Rn c to the n. So take sequences of real numbers or complex numbers. So x1 ... xn. What do you think the multiplication is? The natural, what are the addition? What is the scalar multiplication? The addition is going to be sort of natural. We're going to have x1 ... xn plus y1 ... yn equals x1 plus y1 ... xn plus yn. And similarly, maybe you can guess what the multiplication is. And so what this is saying is every component-wise, addition is component-wise, where each of these components is a copy of the scalar field. And we're going to see cx1 ... xn. We're going to see something similar here. It's going to go over all components, so cx1 ... cxn. And the natural sort of interpretation of this is vectors maybe in 3 space. How do you add a vector 1 here and a vector 2 here? You're just going to follow this guy head to tail, and that's equivalent to adding the components in each. You're going to add in each component. And how do you scale a vector? That's equivalent to changing its length. So this guy, if we multiply maybe by 3 or 4, is going to become this vector here. And so this is sort of the prototypical example. We can't really visualize Cn. And this is sort of natural. And in fact, vector spaces really can be thought of as an abstraction of Rn Cn. And we'll maybe formalize this more in a second. So what are some other examples? Or maybe a counterexample here is to take the empty set. And this is a little bit of a spoiler for the sets, but most of you guys are done with axioms. The empty set cannot be given, and this is not the empty set. Can we get a vector space structure on this? And the answer is no, because there is no element that can be the 0 in V. This such thing does not exist. And so this cannot be a vector space. However, if we take the set 0, we can have a vector space by defining 0 plus 0 equals 0, and c times 0 equals 0 for every c in R. And this is going to be a vector space, because as you can see, in the same way that the 0 set is a ring, maybe, is the trivial ring, we can get all kinds of results. And so this is going to be the right sort of situation. This is the 0 vector space or the trivial vector space. Another example is going to be matrices. Let's say 1, 2, 3, 4, plus 5, 6, 7, 8, 6, 8, 10, 12. Look at that, very nice. Is that right? Yes. So this is some kind of multiplication. We can abstract this to adding in each entry of the matrix. So this guy adds with this guy to get this guy. And for an arbitrary n by n matrix, we can do this to define a multiplication. An addition and multiplication can just be multiplying across all components just like before. And perhaps a more abstract example, maybe one that you might assemble from the sets, is going to be a set of polynomials, p sub n of R, of polynomials a0 plus a1x plus an x to the n with degree less than equal to n. And it has to be this less than equal to n, because in order to have closure of the addition, if we have x to the n plus negative x to the n, for example, we're going to get 0, the 0 polynomial, and this is of degree, really sort of degree negative infinity, actually. But we have to make sure that we can't just be staying in degree n, we have to be in these degree less than n situations. And this is going to be itself a vector space. with the natural sort of addition and multiplication. And perhaps the most abstract sense is take a set A and consider the A in A. So we have a function from A into R that for every A in A, f of A equals, f of A is an R for some R. And so we can define a very sort of natural vector space structure by taking two functions, f and g, and taking f plus g of A equals f of A plus g of A. And we scale by cf of A equals c times f of A. And this is an R, so we can certainly multiply by c. And this is going to always be a vector space. So in general, in sort of a general principle in mathematics, functions from a set into a field, either R or C in this case, or in the sets you might talk about more fields more, but we're not going to concern ourselves with this, form a vector space. And this is going to be really sort of important. And maybe an interesting question is what substructures lie inside vector spaces? So what is the natural definition? We want to have the same sort of operations. We just want to have something smaller inside. And so we're going to say definition subspace. Let V be a subspace, or let V be a vector space, let's say over R maybe, if W is a non-empty subset of V. So W subset V, W not equal to empty set. Then if W is closed under addition and multiplication, under plus C dot, then W is a subspace of V. So equivalently, what this is saying then is that if it's closed under these operations, it automatically satisfies all the same arithmetic, because this just lives inside of the bigger space. So equivalently, what we're really saying is W, this is equivalent to W being a vector space with same operations as V. So, and there turns out to be a very important sort of way to check the ways, because we need to check that both addition and scalar multiplication are closed. And proposition, a non-empty set W, subset W, subset V of a vector space V, is a subspace if and only if for every W, W prime, and W, so for every W, W prime, and W, and C and R, CW plus W prime is going to also be in W. So why is this? Basically what we're going to do is we're going to say that this condition somehow allows us to encapsulate both the scalar addition, the addition and the multiplication rules. So proof, if W is a subspace, closure makes this true by trivial, so trivial, because closure automatically tells us that these guys live in W, and hence this guy also lives in W by closure of the operations. Conversely, if W has these properties, then choosing C equals 1 and W plus W prime, we have W 1 times W plus W prime equals W plus W prime in W for all W prime, showing closure, and taking W prime equals 0, CW plus 0 equals CW in W by this rule tells us that we're closed under scalar multiplication, and hence we're done. And again, sorry for the bad handwriting. Pay attention to the voice, not to the hand, maybe. And so, what are examples of this? Perhaps there are some trivial examples. So, proposition every vector space has at least two subspaces. Can you guess what they are? The first is going to be the trivial vector space 0, and the second is going to be V itself. V itself is obviously a vector space, as is the 0 space, and both must live inside of V, so this must always sort of exist. A more geometric example is maybe consider 3 space again. Consider the plane of things in, let's label these x, y, z. Consider the 2D plane. This is clearly somehow closed because if we just take this is clearly closed under addition of vectors itself, and when we consider this inside of 3 space, this is again going to be closed. And so hence, somehow we have a copy of R2 inside of R3, and this is a subspace. And we will maybe talk about this more example. For a more abstract example, as we talked about, the set of functions on a set is a vector space. So consider the set of all functions f from, so the set of all functions from r to the n to r. This is a vector space. Now, because this is r to the n, consider the set of smooth functions, subset of f infinitely differentiable, I should say. Or maybe we can just say continuous. Yeah, so continuous is maybe a good example of f continuous functions. So continuous functions are, if f is continuous and g is continuous, f plus g is continuous, and scalar multiplication won't change continuity. So this is going to be a vector space. This space, maybe not C, it might be denoted maybe C of Rn. The set of smooth functions, which is infinitely differentiable functions, which is a quite stronger condition, is going to be called C infinity of Rn, maybe. So that's another important vector space, not one we'll talk about. It's going to be one that shows up a lot if you ever look at things like differential topology or more real analysis in the future. And so now let's make a big definition. It's going to be very sort of important. Because we want to deal with this notion of linearity, what is linear? And linear sort of refers to things that are constant coefficients with single variables. So in the plane, maybe, linear is a line through this. So this is going to be maybe y equals ax. Not ax plus b, because it doesn't scale linearly in x. And so as a vector, maybe you might say that this is spanned by the vector 2, this sort of arises from 2, 1, which is this vector here, and then rescaling it to get everything else. So maybe you want to capture these ideas of linearity and of span. And so the important thing is going to be the following definition. Definition, linear combination. A finite sum, finite is important here, of the form I equals 1 to the k, c to the I, v to the I, with c to the I in R and v to the I in V, is called a linear combination. And so we can see why these are sort of interesting objects. Lots of sort of functions appear linearly, and lots of these sorts of interesting objects arise as linear combinations. That's a good example here. Maybe what is the shape? Maybe that's giving things away. Okay, it can wait. But you will see these linear combinations show up many, many times, even sometimes on the sets. Wink, wink, nudge, nudge. Though not until the later ones. But linear combinations turn out to be very, very important because they provide a lot of structure. And so we're going to make a following maybe sort of dual definition of span. Given an arbitrary subset, so not necessarily a subspace, S subset V, the set of all linear combinations of elements in S is called the span of S. And this is sort of all the things we can reach linearly from the elements in S just by taking for xy, x1, dot, 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 so on, xn and S, taking ax1 plus a1x1 plus a2x2, taking all these combinations, this is all the things we can get to. And so what happens when the span is the entire space? If span S equals V, we say S spans V. And so by convention, an empty sum is going to sum to 0. So this sum here is going to be the sum, the empty sum in empty set is going to be equal to 0, and hence the span of the empty set is going to be the 0 vector space. And if span S equals V and S is finite, we will see soon that this is very special. And we are going to say V is finite dimensional. So maybe now let's take a little breather from these ideas of span and talk about something a little more concrete. So we want to ask maybe how can we put, now that we have subspaces, we have these spaces that live inside of vector spaces, such as again this plane inside of R3. Can we add subspaces? Since they live inside of it, can we put them together to get back R3? And maybe the example here is take R3 and take the Z line. So the Z line is clearly going to be itself a subspace, and we're going to have here, maybe I should use a different color, we're going to have the subspace of the 2D plane. But if we identify things x, y, 0 here, these are going to be 0, 0, z, every point x, y, z can be decomposed as x, y, 0 plus 0, 0, z. And hence somehow these guys sort of add together to give all of R3. And furthermore, this is unique. There's only one way to do this. Since this x has to go to this x, this y has to go to this y, this must be 0, this z has to go to this z. And so somehow this is unique. And this is going to be an idea we want to encodify. So the way to do this then is to define the following. Definition: the sum of subspaces A and B is the set A plus B equals A plus B for A and A, B and B. So here, A plus B is the set of all sort of sums, 1 in A, 1 in B. And I claim, and I'm going to leave this as an exercise maybe, exercise A plus B is a subspace, since A and B are subspaces. And you guys can prove that on your own time maybe. And so if we're going to make another definition, if A intersect B is going to be equal to 0, then this sum is an internal direct sum. Internal direct sum. And we're going to write it not A plus B, but rather A O plus B. And this is going to, somehow this condition here is going to give rise to uniqueness. Why? Let's say V equals A plus B equals A prime plus B prime. Then what we're going to have is A minus A prime equals B prime minus B. This lives in B, this lives in A. What is the intersection of A and B? The intersection is trivial. Hence, this tells us A minus A prime equals B prime minus B equals 0. Hence, A equals A prime, B prime equals B. Hence, this decomposition into A and B and A prime and B prime is the same decomposition. And in contrast to the direct sum, let's say A and B are rather arbitrary vector spaces with no connection at all. So A, B, arbitrary vector spaces. We can define a new sum, the Cartesian sum, by taking A O plus B to be a set of ordered pairs A comma B for A and A, B and B. Not all of you have seen set theory before, but for those of you that have, this is exactly just sort of the set theoretic ordered pairs. Instead of taking points along the integer line in here, we can take ordered pairs of integers, and that gives us the integer lattice in the two-dimensional plane. I don't want to do that. It doesn't look like a lattice anymore anyways, but sorry. I'm distracted. And so it turns out that these guys really, we use the same symbol because we can make formal in a sense later that AO plus B is the same. So this is just called a direct sum. You might say external, so external. We might say external direct sum is the same as internal direct sum. And maybe you should convince yourself of this. You should write out sort of maybe an example. Say take R2 and polynomials in two variables. Or maybe what's a better example? Take R4 to be the subset set of sequences in 4 elements. A0, A1, A2, A3. Take a copy of R2 to be given by A0, A1, 0, 0. Take a copy of R2 given by 0, 0, A2, A3. Show that, so let's call this R21, R22. Exercise. Show that R4 is going to be this internal direct product of R1 squared plus R2 squared, R2, 2. And convince yourself that this is the same as taking this, that when you take this sort of construction via the Cartesian product, it's really going to somehow contain the same information. And we might be able to formalize that later with a tool called isomorphism. And maybe a more interesting example that we should do is the following. So recall that an even function is a function r to r is even if f of negative x equals f of x. And we're going to say it's odd if f of negative x equals negative f of x. So here are an outline of exercises. Prove that v sub even, so the set of even functions is a subspace. And similarly for v odd is a subspace. And then I want you to prove that that the set of all functions from r to r, so the set of all these functions is denoted r to the r. Show then r to the r is an internal direct sum of VE and V odd. Okay, and maybe we can now finally get to our last topic, also conveniently our longest topic. Remember I talked about this idea of linear combinations as sort of being the right things to look at linearly, the simplest things in the vector space. The linear structure, turns out that not only are these linear things very important, they're in fact sort of the only things that exist when we choose the right subset S. And so how do we codify this? We're going to use the following definition. Lin independence. So this is going to be linear independence. A subset S of V is linearly dependent if there exists a linear combination such that let's say alpha I v to the I, so AI v to the I equals 0 with not all of the coefficients 0. If all the AI is 0, then trivially the sum is 0. And we're saying it's dependent if there exists some non-trivial combination that still makes the sum 0. And if no subset, if no such set exists, or lin combo I should say, and combo exists, then S is said to be linearly dependent, is linearly independent. And so somehow this is some kind of degeneracy condition, maybe. We can say that if these guys equal 0, then somehow these guys aren't really good enough. And independence is good because the only thing that equals 0 is all of the alpha I being 0. The only combination equals 0 is the trivial combination. And we will also want to maybe work with tuples of vectors instead of just sets of vectors. So let's say v1 ... vk is a tuple. If this is going to be where you say the tuple is independent, this is independent if sort of sum of ai vi equals 0 implies ai equals 0 for every I. So the only combination equaling 0 is all the trivial combination. And these tuples cannot have repeated vectors. So now I guess maybe we should prove a couple of big, perhaps tedious propositions. Proposition A, if S subset V is linearly independent, every subset of S is independent. Can you guys think how to prove that? The answer is sort of simple. If we have a combination of a subset that is equal to 0, so let's say ai vi equals 0, vi in S prime subset S, then this is itself a combination with the vi in S because this is a subset. In which case, since S is independent, this implies ai equals 0. And so this shows independence. Let's say set B then. If S subset V is dependent or spans V, every subset of V properly containing S is dependent. So why is this? So if there is a space, if S has a non-trivial combination that is 0, anything containing S also has that combination, hence is 0. And if S spans V, then if we add anything onto S, so if we add V, if we take the set S union V, since we have S spans V, V is a combination AI Vi of Vi and S. But then take the combination AI Vi minus V. And this is going to be a combination of terms. This is plus -1 in S union V. And this is going to be equal to 0. So this is some kind of non-trivial combination that equals 0, and hence this shows dependence. And part C then is going to be S subset V is dependent if and only if sum V in S is a linear combination of elements in S not including V. So why is that? If we have a sum AI Vi equals 0, then let's take, say, V1 is V, okay? If V1 equals V, then we can pull out the V1, and we have the for Vj in S V. So if we pull out the V1, all of these other guys don't have V in them, and this is going to be some sum equal to 0. So hence V equals the sum negative of the sum. And so it is a sum of, it is a linear combination of elements in S bar V. And similarly, the reverse sort of element shows if we have this, we simply put this on the other side, and we're going to get this non-trivial combination. And the last part is maybe if V1 ... vk is linearly dependent in v with v1 not equal to 0, then some vi is a linear combination of the prior vectors in the tuple. So what this does is basically, I'm maybe going to leave this as an exercise to you, but essentially use part C, but instead of taking this as an arbitrary sum, label this explicitly in terms of the order, and then pull out the first term that fails. So this gives us quite a bit of structure. It tells us a lot of conditions about where dependence can come, where it doesn't come, and such. So now we can make the following sort of key definition that is behind everything. Basis. Basis for V is a subset S subset V such with span of S equal to V. So S is going to span V, hence everything in V can be written as a linear combination, and S is linearly independent. If V has a finite basis, B is finite dimensional. And for example, the trivial space 0 is finite dimensional since it has a finite basis by the empty basis given by here, B equals. So why is a basis important? The answer is going to be the fact that this guarantees everything can be written uniquely in terms of the basis. And let's see why. Let's say we can write V as sum of Ci Vi for some Ci, and let's say we can write it for Bi Vi. Let's say the Vi live in the basis B. Let's call this B, not S. If this is true, then we're going to have Ci minus Bi Vi equals 0. But what do we know? We know S is linearly independent. Hence, the only combination for that is 0 is the trivial combination. Ci minus Bi equals 0, and Ci equals Bi. Hence, this is the same expansion. And concretely, what is an example of this? Take R3. Every vector in R3 can be written as a part in the x component, a part in the y component, and a part in the z component. And if we think about this in terms of coordinates, A, B, C can be written as A times 1, 0, 0, where A is a constant, plus B times 0, 1, 0, plus C times 0, 0, 1. And this is going to be some kind of unique expression. And so somehow, independence provides this uniqueness of the expansion, and spanning tells us it gives us the whole set. And we can actually order a basis using these K tuples that I talked about earlier, and at which point, if we order it in something like this, we can compactly write our vectors A, B, C. And this kind of notation will be very important when we talk about matrices later. So how do we know that this works? We need to know sort of, these bases are very interesting. If we can find a basis, then we can write everything expansions. And maybe as another example of a basis, take the sphere, or maybe take R3 again, I should say. R3, but instead of identifying things by x, y, z, identify a point by an angle theta, a radius r, and a height z. Or maybe take a point and label it by an angle theta, then another angle phi, and finally a radius r. This is going to be cylindrical coordinates, where we call this cylindrical because if we think about it, these r and theta give us a circle and the z gives us a height, and that gives us sort of a cylinder-like parametrization space. And here we have a sphere because we're only doing one distance r, and then there are two angles parametrizing us along the sphere. Cylindrical, spherical. Notice all of these have three parameters. So this has r, theta, phi. This has r, theta, z. It's not a coincidence they have three things. We want to show that if we can write things uniquely in some kind of one basis, then every other basis has the same number of elements in finite dimensions, maybe. And so the following lemma is going to be the critical fact. Lemma. If V is spanned by n vectors, every subset of V with greater than n vectors, so more than n vectors, is dependent. How does that work? So proof. This is going to be probably the only sort of non-trivial proof we have. Let S subset V have greater than n vectors. Then S contains, algebraically, this is, we have W1 dot 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 Wm with m greater than n. Since V1 through Vn spans V, since this is spanned by n vectors, we can write each Wi as a linear combination. So we can write Wi equals sum m, k equals 1, let's say beta ik, vk. And then if we want to show independence, we want to show there exist not, to think about independence, we need to think about linear combinations of the Wi. So we need to think about ai such that the sum I equals 1 to the n of the alpha I, maybe, so let's go, it's alpha, not a, alpha I, Wi equals 0. And we want to show that all these alpha I, that there exists some kind of non-trivial alpha I to show dependence. So how do we do that? The answer is going to be to write this out. 0 equals sum n, I equals 1, alpha to the sub I, sum k equals 1 to the m, beta sub ik, vk. And this is going to be some kind of double sum, right? It's going to be sum over I equals 1 to the n, sum over j equal, let's say k equals 1 to the m, alpha I, beta the ik, v to the k. But now we can swap the order of the sum. We can sum instead over k equals 1 to the n, to the m, and pull out the beta ik. Or we can't pull it out just yet, actually, but we can do this, and then we can sum over k equals 1 to the m of beta ik, alpha I, and then v to the k. So basically we're grouping these guys and we're swapping the order of the sum. And somehow this is going to be this system of equations then is going to be a solution. Because we want to show this is a solution in V, and the V span the space, and the V are, how do I want to say this? Maybe just consider this system, we want to show non-trivial alpha I solution. If all the alpha I are 0, this is equal to 0 pretty trivially. So consider the system m k equals 1, beta the ik, alpha I equals 0. So we have n variables here. We have m equations here, m equations, and we have n variables because we know our beta ik. N variables alpha 1 dot 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 alpha n. And m greater than n. I think I misspoke. So this should be an n here, not an n. So this is an n, this is an n. So we have n equations, and we have m unknowns. But we know that m is greater than n. So more unknowns than equations. The theory of matrices, or more generally sort of just math in general, tells us that when we have more unknowns than equations, we're always going to have some kind of non-trivial solution when the coefficients on the right are 0. As an example, maybe take x plus y equals 2, 2x plus y equals 0, and or maybe x plus y plus z equals 0, and 2x plus 5y plus 3z equals 0. Does there exist a non-trivial solution to this? The answer is yes. Why? Whenever we choose x and y, we can always choose a z to make this fit. Or whenever we choose x, we can choose y to make this work, and then we can choose z to make this work. Somehow we can play with these variables to reduce it to the case where we always have some kind of sort of free variable to choose that makes the system 0. This is formalized by the theory of matrices, but that's not really required. You can check the appendix. But this tells us that there is some non-trivial solution. There exists non-trivial alpha I, which tells us then that v1 dot 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 vn is, or rather the set w1 dot 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 wm is dependent. So any set with m greater than n terms is dependent. And that completes our proof. And now that we have this, we can finally get to the main sort of result. Proposition: if V is finite dimensional, all bases have the same number of elements. Proof. So the above proposition tells us if n spans V, m greater than n is dependent. Since a basis has to span V, let's say basis 1 has m elements, basis 2 has n elements. So this proposition from above tells us that since basis 1 spans V and basis 2 is independent, n is less than or equal to m. But doing the reverse thing tells us that m is greater than or equal to n. And hence we have n equals n, when both of these are actual numbers. Hence finite basis. And so this allows us to make sort of clear a constant composition. This makes the following thing well defined. Let, given V finite dimensional, define dim V to be the number of elements in a basis. So in R3, maybe, what is the number of elements in a basis? 3. In polynomials of degree less than or equal to n, what is the number of elements in a basis? We have a0 plus a1x plus dot 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 plus an xn. And I think you can convince yourself pretty easily that 1 dot 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 x to the n is a basis. Hence, there are n plus 1 elements in a basis. And this is a good place to leave it off for now. I think this recording is actually pretty bad. So, maybe tomorrow I will record a new one. If not, this is what's going to go up for now. Thanks.